All right, so it's 11:35. I wanted to use the opportunity to thank you for joining the meeting today. You're welcome to today's pre-seminar. My name is Shay Balogun, and I'm Assistant Professor Sinan Keten. We're chairing this meeting. And as you know, the focus of this pre-seminars this quarter is on soft materials, in particular, the mechanics of soft materials. So in a few minutes, I'll bring up our speaker. But before then, I just want to get through some particulars. Please post your questions and comments in the group chat, and then I can read them out at the end of the lecture. And also at the end of the lecture as well, you're welcome to unmute your microphone and ask questions as you please. So our speaker today is Ziwei Wang. He's a student, is a third-year PhD student in the mechanical engineering department. Also, he's a research graduate student in my group. And I'm particularly excited to introduce him today and to also have him share some of the work he's doing in the area of mechanics of cornea tissue. In terms of his background, he got his master's degree in the Beijing Institute of Technology in China. And then since then, he's joined us at Northwestern. And he's a productive member of my research group. So I'm excited to bring him up. Ziwei, please proceed.
All right, thank you, Professor Balogun, and thank you everyone, and welcome to this talk. So it is a great pleasure to have this chance to talk about my ongoing research on the corneal mechanics characterization. So as the title says, the corneal mechanics is tied to diagnosis of glaucoma. So I want to start my introduction by talking about some basics of this eye disease. So glaucoma is the eye disease that is the one of the leading causes of blindness. And normally in the eye, the regular circulation of the aqueous humor in the anterior chamber ensures the functionality of the eye. So the glaucoma happens when the trabecular meshwork here, that the trabecular meshwork blocks the circulation and the pressure in the eye starts to build up. So the diagnosis of glaucoma mainly relies on the intraocular pressure test. And one of the widely used clinical method is the ocular tonometry. So basically, the tonometer has a rod that we can use this rod to press the cornea, that we can get the force, reaction force. And based on this imperfect law, that we can calculate the pressure or the intraocular pressure in the eyes. However, this method has some limitations. So first, it has low accuracy for the eyes with abnormal thickness or the pressure levels. And also the arrow is large for the eyes that went through the LASIK surgery or any other damages. And also this method does not review the true mechanics of the cornea, which may be crucial to the IOP detection and the understanding of the glaucoma progression. So researchers are starting to look for the new non-invasive and non-destructive method that can estimate the intraocular pressure in the eye and also consider the corneal mechanics. So intuitively, the tensile test is a simple and accurate way to measure the elastic properties such as Young's modulus. So we can cut the corneal tissue from the eye and mount it on the test machine to get the stress versus strain curve. However, this method is destructive and can only be done in the ex vivo state. So that means in the in vivo state, we have the presence of the aqueous humor and also the presence of other boundary conditions. And this these conditions will be neglected in the tensile test. And obviously, this method cannot be used in the clinical uses. So for non-invasive purpose, so people managed to characterize the mechanics by using elastography. So in this study, they immerse the eye in the water, and the eye is mechanically excited by the ultrasonic probe. So the ultrasonic probe can capture the excited wave propagation. So the wave propagation in the cornea, and also to detect the wave speed. And the wave speed can be used to infer the basic Young's modulus through a simple mechanics model. So this method is non-destructive, but it also has some limitations. So first, the eye has to be immersed in the water for the acoustic coupling, so which is not very convenient for the clinical use. And also the imaging resolution is pretty low. It's about 150 microns. And also you can see from the wave field images that the resolution was not pretty. So to make the improvements on this, people start to explore the another method called the optical coherence elastography. So this is another non-invasive dynamic test that has been used for characterizing corneal mechanics. So in this study, the researchers they used the piezo actuator, which is this green dot. This is the piezo actuator that can generate the acoustic waves in the cornea, and they can use the this optical coherence elastography method to detect the wave field. The wave field travels in the or the wave travels in the cornea, and by using the dispersion relationship or the dispersion model, they managed to estimate the Young's modulus and also the viscosity. And this method is pretty good. It is non-invasive with very high resolution, 30 microns, lateral resolution of 30 microns. But the problem here is that the estimated Young's modulus, the value is far away from the results from the tensile test. So in the tensile test, people get the value of the Young's modulus around 1 megapascal to 10 megapascal. This value is way lower than that value. So it is crucial for us, although this method, the experimental method is good, but still we need to build a better mechanics model to describe the material behaviors in an accurate way, so that we can have a better estimation of the elastic properties of the cornea. So our research aims to develop an accurate method for corneal mechanics. So this comes in two parts. First, we will use the OCE method, as aforementioned, to generate the acoustic wave in the cornea and also detect the dynamic response, which is the displacement field in the cornea. So the other part is the mechanics model. We know that the dynamic response is dictated by the corneal mechanics. So the second part is to build a corneal model that can describe the dynamic behavior. And the core of this dispersion model is the corneal mechanics model. We will have to consider a proper material model and the boundary conditions in the in vivo state. so that we will have the comprehensive description of the corneal behavior. And our ultimate goal is to use this information to estimate the intraocular pressure that can help us diagnose the glaucoma. So our setup consists of three major parts. The measurement setup has three major parts. So for the dynamic mechanical actuation, we have a function generator that can generate harmonic signals. This signal will drive this piezo actuator at a certain frequency. So this actuator will be put in contact with the sample surface so that the mechanical energy can be transferred to the sample to excite the dynamic behavior of the sample. So in this case, the sample is the cornea. And because we want to study the contribution of, or the influence of the presence of the internal pressure, so we have another setup, another part to control the pressure in the eye. So we use a simple water column, and this water column is connected to the internal chamber of the eye, so that by raising the level or lowering the level of this water, of the water in the water column, we can control the pressure in the eyes. And for the detection parts, we will use the OCT and OCE system here. So OCT is the optical coherence tomography. That basically the sample will be illuminated by the laser, and the internal structure of the sample will be resolved based on the backscattering signal. So this picture shows the internal structure of the hydrogel we built previously in the lab. So for the OCE parts, which is the optical coherence elastography, so it's similar to the OCT, but this measurement reviews the dynamic behavior or the wave fields in the structure that excited by the external source. And as you can see in this movie, the blue stripes and the red stripes indicates the displacement, the vertical up and down displacement in the sample. So if we put the excitation source right here, then we can see the wave propagating in the sample along the lateral direction or the x direction. So the OCE measurement in our setup is a little bit tricky, since we know that we want to generate a wave travels at several kilohertz frequency. And the commercial OCT system we use cannot reach the high imaging speed. So we also have to set up the trigger process to synchronize the measurement. So for 2D OCE measurement, it consists of multiple vertical scans, where we call the A scans, and along the customized scan path. So for each vertical scan, the OCT system will be triggered twice. So this is the trigger signal. It will be triggered twice based on each received sync signal from the signal generator. So the profile difference between the two triggered events will represent the displacement amplitude within that interval. So through this process, we will repeat this process for each column, and eventually we will have the displacement field that looks like this. So this freeze displacement field will tell us the wavelength or the wave speed at this actuation frequency. So for the mechanical modeling parts of the cornea, we also have to consider two things. So the first thing is the structure of the cornea. So actually the cornea is a multi-layer system and the stroma layer accounts for 90% of the whole thickness. So we can assume that the mechanical behavior of the cornea is dictated by the stroma layer. And also we know that about 78% of the cornea consists of water. So we can assume that the cornea is nearly incompressible. So our first assumption is that the cornea can be modeled as an isotropic and incompressible material with only one parameter to be determined. And although on the subscale level, we know that the stroma consists of hundreds of layers of lamella with fibrils oriented in different directions, which could be the source of the anisotropy. But to keep it simple for the start, we use the isotropic model first, and we will see if it will be sufficient to describe the dynamic behavior of the cornea. So another thing to consider is the in vivo state of the cornea. So specifically in this case is the presence of the intraocular pressure. And we think that the intraocular pressure will induce the tension in the corneal layer. So it's like the inflated balloon that if you blow the balloon, then the internal pressure will create a tension in the membrane that can affect the stiffness of the membrane. Also, the deformation, the intraocular pressure-induced deformation may trigger the hyperelastic behavior of the cornea. So maybe the mu and the lambda, so the two elastic constants, may be modulated by the pressure as well. So to connect our cornea model with our OCE measurement, we will use the elastic dispersion relation that describes the dynamic behavior and which is controlled by the material model. So in the experiment, we mechanically excite the sample at a frequency f, and we will detect the displacement field, and we run the displacement field through the Fourier transform process. We'll be able to get the spatial wavelength and wave speed at this frequency. And by sweeping the frequency in a certain range, we can obtain a dispersive relationship between the wave speed and the frequency that describe the dynamic behavior of the cornea at this frequency range. We will then build a dispersion model that accounts for our previous assumptions, including the isotropic material properties and the residual stress. By applying the boundary conditions and also the displacement solutions, we can solve the dispersion relationship between the wave speed and the frequency. So the whole idea is to fit this model to the experimental data and to predict the unknown parameters, including the lambda mu and residual stress sigma. So To study the influence of the pressure, we made some rubber membrane samples in the lab, and we mount these membranes on the cavity. And by pushing water into the cavity, as you can see, the rubber membrane will be dramatically deformed. We started with the rubber sample because it's more controllable compared to the bio samples. And as you can see, the OCT image shows the topography of the rubber membrane, that we observed the significant thickness change from 480 microns at 0 Pascal of the pressure down to about 100 microns when the pressure is as high as about 900 Pascals. So the measure here are the displacement fields at 3 different pressure levels, 0 and 600 and 900. The actual frequency, the actuation frequency is from 1 kilohertz to 10 kilohertz. The displacements here are in the phase angles, so which is related to the wavelength of the laser. So we can apply a simple relationship to get the real displacement. But here we are not interested in the absolute displacement, but we are interested in the wave speed. And this profile shares the same wave speed information with the real displacement field. So we can then plot the measured dispersion in black dots for 3 different conditions. And we here compare 2 different models. One is the isotropic model without the residual stress, and the other one is the isotropic model with residual stress. So without residual stress, which are depicted in the red dashed lines, as you can see, the model fit the data pretty well when there's no pressure, but there's a large fitting error that we can see at high pressures. However, when the residual stress is included, the fitting improved for all pressure levels. So the improvement of the model, as we can see, is mainly at the low frequency range. And I think this can be explained by the simple plate model, a stress plane model. So this is the wave speed in terms of the fractal rigidity, the residual stress, and the wave number. So at 0 frequencies, we can see that the residual stress act as an offset to the wave speed. So this tells us that the pressure will induce the residual stress that can be crucial to the correct modeling of the cornea that can help us predict the properties such as Young's modulus in a more accurate way. So moving on to the corneal samples, we collected the fresh pig eyes from the local slaughterhouse for our experiment. We insert the syringe in the eyes to control the pressure in the eye. So the pressure was modulated from 10 millimeter of mercury to 35 millimeter of mercury. And this covers the range of the IOP in the real eyes. And we can see that the thickness of the cornea didn't change too much in this case. So again, we have the similar displacements with similar features as we see in the rubber membrane samples. We can see that by increasing the pressure, the wavelength becomes longer. That means the pressure, the increase in pressure has a stiffening effect on our cornea However, when it comes to the model fitting, it is hard to tell which is better or worse visually for the model with or without residual stress. And another thing to note is whatever the model we use, the predicted Young's modulus, the values are way lower than the reported values in the tensile test. So here we have the Young's modulus about less than 100 kilopascal, but we know that it should be around 1 to 10 megapascal. So, and also another thing to notice is that at high frequencies, we saw that the wavelength comparing to the thickness of the cornea is pretty low. So we'd expect this wave to propagate as a surface wave. That means the displacement field should be confined near the top surface of the cornea. But that is contradictory to what we observe in the experiment. So we have to take a step back and look at our modeling. So this again is the anatomy of the cornea, and as I mentioned earlier, the stroma consists of hundreds of layers of lamella, and so the properties in the stacking is like you have many plates stacking together in vertical direction, and the properties in the stacking direction can be very different from the in-plane properties. So with that, the stiffness matrix can be rewritten as this. So if we treat the 1-2 plane as the isotropic plane, then we will have different stiffness matrix comparing to the isotropic matrix. So for the longitudinal part, we have 4 parameters: lambda, mu as a traditional as the isotropic parameters. And we also have C13 and C33 that represents the modulus in the vertical direction. But if we apply the incompressible condition to the model, then we will know that C13 and C33 has to be close to lambda. So here we can treat the longitudinal part as the isotropic part. So the shear part will have 2 shear moduli. The mu or the C6 is the shear modulus in the transverse plane, 1-2 plane, that is parallel to the lamella. And we will have C44 and C55, 2 shear moduli in vertical planes, which are parallel to the 3 axes. So with this modified transverse isotropic model, the simulated displacement field now matches the experimental data. And it's very clear that the isotropic model cannot describe the dynamic behavior of the real cornea that we observed in the experiment. And also for the model fitting, we now have a range of predicted Young's modulus that are comparable to the tensile test. So now we're on the megapascal level of mu, so they're very close to the tensile test. So now we know that the transverse isotropic model is pretty necessary for describing the dynamic behavior of the cornea. And this is where we are right now. But moving on, we still have some improvements to make of our model. So The first one is the viscosity. So here we can see that from the displacement field in the experiment, we observe the amplitude decays along the wave propagation path. But if the viscosity is not included in the model, then we will not be able to describe this decaying behavior. And also we observe the rising trend of the dispersion in the experiment, but this trend was not captured by the model. So we are going to apply a viscoelastic model to our present model by introducing a dynamic shear modulus. You see the dynamic shear modulus is now frequency dependent and is proportional to the frequency. That means the amplitude of this shear modulus will increase with the increase of the frequency. We had some previous results on the hydrogels, and we compare the two different models, the viscoelastic model and pure elastic model. And we observed that the viscoelastic model will have a higher wave speed at high frequencies. So that might help us to compensate this rising trend we observed in the experiment. And the other thing to consider is the nonlinear elasticity of the cornea. So in our fitting process, whether it's G or mu, we saw that they will change with the increase of the pressure. But keep in mind that we don't have the proper hyperelastic model to describe the behavior. That means these parameters are just fitting parameters that were not confined or constrained by the nonlinear material model. And the if we have the proper elastic model, hyperelastic model to confine these parameters, then maybe the presence of the residual stress will be crucial to the model to help us improve the accuracy of the model fitting. So for the next step, we want to study the hyperelasticity of the cornea via tensile tests, and we will decide whether the residual stress should be considered. So back to our research problem, we want to estimate the intraocular pressure of the eyes. So from our measurement, we can obtain the topography or the geometry of the cornea through the OCT. We can obtain the dynamic response of the cornea from the OCE measurement. We will have this as the input to our full-scale corneal model. So we plan to build a full-scale corneal model, which has been done by the other researchers, but our contribution here is that we will improve our corneal mechanics model to improve the accuracy of the material model in the full-scale corneal model. And through the corneal model, we will try to estimate the intraocular pressure to achieve the equilibrium state. And also, we will consider other non-mechanical factors through the demographic study to account for the gender, age, and race, etc. That would act as the correction factor to our model. So all involved are the work on the cornea. But here I want to show that our method can also be applied to other soft materials. So this is the collaboration work with Professor Bao in the Department of Molecular Biosciences, that we use the same method to characterize the properties of the human skin tissue. And we know that the human tissue has two layers, the dermis layer and the epidermis layer. So if we can measure the dynamic behavior of the dermis and infer the Young's modulus or the elastic properties of the dermis, then we can characterize the artificial epidermis, grow on the dermis, and predict the Young's modulus through a dispersion like this. So we have achieved we have managed to predict the Young's modulus of the artificial epidermis on the dermis. That means the method is transferable to other material testings. And to sum up my talk, so the problem is to identify the true intraocular pressure in the eye to help us diagnose the glaucoma. And the method we used is based on the OCE dynamic test with a stress dispersion model. And we first tested on the rubber sample, and we knew that the residual stress is crucial to the modeling, and the presence of the IOP is crucial to the dynamic behavior of the rubber. Then moving on to the cornea, we know that a simple isotropic model won't work, but we have to consider the transverse isotropic model. This worked well with our data and the observation from the displacement field. And moving on for the future studies, we want to include the viscosity and the residual stress to our full-scale model, and use that full-scale model to estimate the true intraocular pressure, which is our original research problem. And lastly, I want to thank Professor Baligan and all the other group members for their support. And I also want to thank Professor Corneal from Civil Engineering and Dr. Tana from Madison, from the Madison School for their support and collaboration in our corneal work. And with that, thank you all for attending this talk, and I will take any questions you may have.
Thank you, Ziwei, for your talk. The floor is open for questions, but I'm going to start with a question from Professor Mark Johnson. And his question is, the diagram showing pressurization of the eyes showed that this was done with water. Is that right? Or was it done with saline?
It was done with a saline solution. Because if we use water, then the cornea will hydrate, so saline will work better.
And Professor Johnson, you can unmute your microphone if you have a follow-up question.
No, that's the answer I wanted to hear. I was concerned about corneal swelling, so that sounds like a great answer. Thanks.
Welcome.
Thank you.
So the floor is open for questions. Okay, maybe I can lead with the question. So you've discussed several other contributing factors that can influence your estimated properties. I do have a concern about curvature. So can you comment about curvature? And also, how do you plan to validate the measurement? So beyond, say, comparing the results to tensile testing. So if we go back to the rubber membrane, for example, how do you plan to validate those results?
So I guess the first question is the curvature effect, and I think it is obvious that at the high pressure level, the rubber will become like a balloon. That a curvature may have to be considered, but in reality, the when this film is too thin, that the thickness comparing to the radius of curvature is too small, then the curvature effect can be neglected. So in this case, the thickness is only about 100 microns, which is way smaller than the radius of curvature. So the curvature effect can be neglected. And to verify this result, I think clearly the tensile test will be easier to do. And beyond that, I don't have a better idea to verify the model. I think tensile test should be a way to go and should be accurate.
Can I follow up on that same line of questioning?
Yes, please.
So just in terms of, and you gave a nice explanation for why you needed to take into account the anisotropy of the cornea, which I would have expected, and sounds like you got a nice result on that.
Yes.
But there's a couple other characteristics of the cornea that I just wonder if they'll make any difference. The cornea, of course, is a poroelastic material. I doubt that on the time scales of your measurement that makes much of a difference. I would still think that your incompressible assumption would be correct. So I doubt that makes a difference. But the other thing that I thought of is that, of course, the structure of the cornea is such that you have these tense collagen fibrils surrounded by water. And when you measure the modulus of a material like that, the tensile modulus tends to be much different than the compressive modulus. That if you compress a material like this, it actually compresses pretty easily as compared to stretching it. Would that have any effect on your measurements?
Yes, that's a pretty good question. I think I think I understand the question. So if we do the tensile test and the compressional test, we will end up with different.
Yeah, we've done it on the sclera, and I assume the cornea will be very similar. I'm just wondering how that would affect your measurement. I don't claim to know the answer to this. It may or may not have an effect. I'm just curious what might happen.
To be honest, I'm not pretty sure whether they will have the effect or not, especially in our dynamic test.
Like I said, I'm not sure either. So,
yeah. So maybe if I can follow up on that, can you comment on the sort of scale of your displacements, and at the displacement scale, right, of your measurements? Do you anticipate those issues may be important? So tensile or compression at the particular displacement scale of your measurements?
The displacement, so the excitation, we use the piezo actuator to excite the mechanical waves, and the amplitude of the actuator is about 1 micron. So considering the viscosity damping effect, I would say the displacement in the cornea will be definitely will be lower than 1 micron. So maybe several nanometers. And I don't know, comparing to the scale of the collagen fiber, to be honest, I don't have a good answer whether this level of displacement may trigger some abnormal behavior of the fibers.
Right. Yeah, definitely. It's a great point you raised that we can take a look at. The only point I'm going to follow up on is the fact that these displacements are very small. The strains are very small. So they're certainly less than, less than 10 to the -3 in terms of the strains. So we're not exactly sure what role this would play in this small strain limit. And then the other issue is that indeed, we're using a highly simplified transversely isotropic model. And so we may need to revisit, how C33 is defined, some of the elastic constants in the transverse isotropic model. And we can follow up with you, Professor Johnson, on, follow-up discussions to sort of review those questions in detail. But that's a valid point you raised.
Yes.
So happy to follow up, but your answer sounds perfectly good to me, that in the very small strain limit, you're really the fact that the compressive modulus and tensile modulus are different, you're right, that would be at higher strain levels in both directions. So you're absolutely right that likely not to make a difference. That's a perfectly good explanation for me.
Thank you. Okay, so it's still it's 12:21. We have time for more questions. Can we get a question from students? Okay, Sinan is going to ask a question.
Yeah, I was going to ask for diseases of the cornea as well as its mechanical behavior, how important is the interface between the fibers and between the layers? In other words, are there particular concerns about a continuum-like representation of these fibrous systems, or because of the fact that it's difficult to capture what exactly might be happening at the interfaces? Or do you think it's adequate for most purposes, at least for elastic property predictions, things like that?
So I think physiologically the interface between, such as the epithelium, the interface between the epithelium and the stroma may change in the glaucomatic eye. But for our measurements, you have to see that the displacement field or the wavelength is much larger than the scale of this thickness. So I think it is really hard for us to say whether, or to determine the properties of the interface, because the wavelength is larger than the thin layers such as the epithelium or the endothelium.
Okay. Well.
Yeah, but it could be important. It's just that the scale of the measurements is much longer.
Yeah.
Right. In fact, I can imagine that, as most of these modes are shear-dominated, those interfacial properties would influence any sort of sliding deformations that you see between the lamellae, or even between the fibrils themselves. So those properties would definitely be important, but it's a question of how you access those properties. There may be other methods with higher resolution that may be able to capture that.
And maybe you mentioned this, what's the pitch angle between these lamellae? Are they laid up in a specific rotation angle between each layer, or is that well known?
Based on my readings, I think they are pretty random between layers and layers. So that's why we approximate that plane as an isotropic plane.
Yeah,
I'm not sure that's true. I think they're actually fairly organized. I think they're about 60 degrees from one to the next.
60 degrees? Oh, okay.
I could be wrong on that, but I think it's more organized than that. The refraction of light that goes through there is very carefully controlled by the cornea, so that the second harmonic disappears. So I think they're more organized than that.
Yeah.
that makes sense. Yeah. Thank you.
Thank you. That's a good point.
Thank you. We also have time for more questions. Maybe a student would have a question. Any students? Okay, no students. Do you, just to follow up on the last question, so do you anticipate that the organization of the lamella plates may be position dependent, maybe so for example closer to the center of the cornea and then and away from the center of the cornea, towards the towards the edges? Have you seen any discussion in the literature about that?
Uh,
Well, it's okay if you haven't seen any, that's fine.
yeah, I don't have a clear memory on this.
That's fine. That's fine. That's fine.
Can I ask another question out of curiosity?
Yes.
This might be a very naive question, so I apologize if it is so. So these fibers, we kind of think of them as lying in some lamella, but I wonder in each plane, can the fiber orientation change at all? Like in liquid crystals, you have oriented phases or domains, but then there's like regions where you have almost like a grain boundary where the fiber orientation is different in some other part, or are they actually continuous fibers throughout the freestanding?
So based on my readings, it seems that in each layer of the lamella, the fibers are all running parallel to each other. So in each layer, they will have their preferred alignment, direction or orientation alignment. So I think they observed that through some microscopic method. So that I can be sure about this. But I'm not very sure about the alignment between layers and layers. So maybe they're random, but if that's the case, then maybe we cannot use this isotropic plane approximation. Maybe we also have to modify this part in the future.
Thank you, Ziwei. So there's just 2 more minutes. If there are no other questions, I guess I'm going to stick around for a little bit to see if there's any other questions. Any questions? Okay, if there are no questions, I want to thank you for joining the meeting today and also for the interaction we had with our speaker. We'll close the session and we look forward to the next lecture next week, Wednesday. Thank you so much. And thank you, Ziwei, for presenting a beautiful talk. Thank you.
Thank you. Thank you.
Thank you, Ziwei. Great talk. Really enjoyed it.
Thank you.